Hello there, and welcome. Tonight, we're going to take a journey. Not just any journey, but the longest one imaginable. We're going to travel through time itself, from the very first moment the universe blinked into existence, all the way to this present second as you're watching this video. It's a story that spans 13.8 billion years, and somehow, impossibly, we're here to tell it. Think about that for a moment. Every star you've ever seen, every mountain, every ocean, every living thing, every atom in your body, all of it has a history that stretches back to the beginning of everything. And what's remarkable is that we've actually figured out much of this story. Through careful observation, brilliant reasoning, and a lot of hard work, scientists have pieced together the biography of the cosmos itself. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now sit back, relax, and let's begin at the beginning. Our story starts 13.8 billion years ago, though starts might not be the right word. There was no before the Big Bang, at least not in any sense we can understand. Time itself began at this moment. Space began. Everything we know, everything that exists, compressed into a point smaller than an atom, infinitely hot, infinitely dense, and then it happened. The universe began expanding, not exploding into empty space like a bomb going off. There was no space for it to explode into. Space itself was expanding, carrying everything with it. In that first incomprehensibly brief instant, the universe was nothing like it is today. The laws of physics as we know them didn't exist yet. The four fundamental forces we observe now, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. But this unity didn't last long. Within the first trillionth of a trillionth of a trillionth of a second, something extraordinary happened. The universe underwent what scientists call inflation, a period of exponential expansion that increased the size of the cosmos by a factor of at least 10 to the power of 26. To put that in perspective, imagine a marble suddenly becoming larger than the entire observable universe. That's how dramatic inflation was. Why did this happen? Scientists currently think that inflation was driven by a special kind of energy field, though the details are still being worked out. What we do know is that inflation solved several puzzles about why the universe looks the way it does today. It explains why the universe appears so uniform when we look in different directions, and it explains the subtle variations in density that would later become galaxies and clusters of galaxies. After inflation ended around 10 to the power of negative 32 seconds after the Big Bang, the universe was still unimaginably hot, about 10 to the power of 27 degrees Celsius. At these temperatures, even the basic building blocks of matter couldn't form stable structures. Instead, the universe was filled with a roiling soup of fundamental particles and energy, with matter and antimatter constantly appearing and annihilating each other in violent bursts. As the universe continued expanding, it cooled. And as it cooled, something crucial happened. The four fundamental forces separated from each other, each taking on its distinct character. First, gravity split off, then the strong nuclear force, and finally electromagnetism separated from the weak nuclear force. The universe was beginning to develop the rules that would govern everything to come. By the time the universe was 1 second old, just 1 second, it had cooled to about 10 billion degrees. Still incredibly hot, but cool enough for the first simple atomic nuclei to begin forming. This was the era of nuclear synthesis, when the basic elements that make up our universe were forged. In those first few minutes, protons and neutrons combined to form the nuclei of the lightest elements. Hydrogen was most common, making up about 75% of all matter. Helium came next, at about 25%. Tiny amounts of lithium and beryllium also formed. And that was it. Nothing heavier could form because the universe was expanding and cooling too quickly. It's worth pausing here to appreciate something profound. Every hydrogen atom in your body, in the water you drink, in the air you breathe, those atoms were formed in the first minutes of the universe. When you look at the stars, you're seeing matter that's been around since almost the very beginning. But here's a question. If atoms were forming, why couldn't we see anything yet? The answer lies in what the universe was still made of. Even though atomic nuclei existed, the universe was still far too hot for electrons to settle into orbit around them. Instead, the cosmos was filled with a dense fog of charged particles and photons, light particles that were constantly bouncing off each other. Imagine trying to see through the thickest fog imaginable, where light can't travel more than a tiny distance before hitting something. That was the early universe. This foggy state, called the plasma epoch, would last for hundreds of thousands of years. The universe was glowing, radiating energy in all directions, but there was nowhere for that light to go. It just kept scattering off particles, trapped in an endless cosmic pinball game. Fast forward to about 380,000 years after the Big Bang. The universe has expanded enormously, and its temperature has dropped to about 3,000 degrees Celsius, still hot enough to melt any metal we know, but cool enough for something momentous to happen. Electrons, which had been zipping around freely, finally slowed down enough to be captured by atomic nuclei. Hydrogen and helium atoms formed in earnest. This event is called recombination, though that's a bit of a misnomer since the electrons and nuclei had never actually been combined before. But the name stuck. The effect was dramatic. With electrons now bound to atoms, photons no longer had charged particles to bounce off. The fog lifted. The universe became transparent. Light could finally travel freely through space. This moment, when the cosmos went from opaque to transparent, is sometimes called the moment the universe turned on. That ancient light is still travelling through space today. We can detect it as the cosmic microwave background radiation, a faint glow coming from every direction in the sky. When scientists study this radiation, they're literally seeing light that has been travelling toward us for more than 13 billion years, light that was emitted when the universe was just a baby. It's the oldest light we can ever hope to see, our earliest baby picture of the cosmos. But even though the universe was now transparent, it was also entering what scientists call the Dark Ages. And yes, that's exactly what it sounds like. After recombination, the universe was filled with neutral hydrogen and helium gas, spread fairly evenly throughout space. There were slight variations in density, places where the gas was a little thicker, places where it was a little thinner, but no stars yet. No galaxies, no sources of visible light except the fading afterglow of the Big Bang itself, which was rapidly shifting into the infrared as the universe expanded. This was a dark time, literally. If you could somehow exist in the universe during this period and look around, you'd see nothing but darkness in every direction. The only light would be the dim, invisible, infrared glow of the cooling universe itself. But beneath this darkness, something was happening. Gravity was at work. In regions where the gas was slightly denser than average, gravitational attraction was pulling in more matter. Slowly, over millions of years, these denser regions grew denser still. Gas clouds began to collapse under their own weight, forming clumps and structures. The Dark Ages lasted for about 100 million years. It might not sound like much compared to the billions of years that would follow, but think about it this way. That's longer than the dinosaurs ruled Earth. It's an enormous span of time for a universe sitting in darkness, waiting for something to happen. And then, finally, something did happen. The first stars began to shine. Somewhere between 100 and 200 million years after the Big Bang, the first stars ignited. These weren't stars like our Sun. They were monsters, enormous, hundreds of times more massive than our Sun, burning millions of times brighter. Scientists call them population 3 stars, and they were made of the simplest materials, just hydrogen and helium, with virtually no heavier elements. Why were these first stars so massive? Without heavier elements to help cool the collapsing gas clouds, only the largest clouds could collapse far enough to ignite nuclear fusion. The result was a generation of stellar giants, blazing with fierce blue-white light, each one hot enough to blast its surroundings with ultraviolet radiation. This radiation had a profound effect on the universe. It began rionizing the hydrogen gas around these stars, stripping electrons away from atoms once again. Slowly, over hundreds of millions of years, bubbles of ionized gas grew around stars and clusters of stars. These bubbles eventually merged, and by about 1 billion years after the Big Bang, the universe had completed reionization. It had gone from neutral to ionized, transformed by the light of countless young stars. But here's the thing about these massive first stars. They lived fast and died young. A star like our Sun can burn for 10 billion years. These population 3 giants might last only a few million years before exhausting their fuel. And when they died, they didn't go quietly. The most massive stars ended their lives in supernova explosions, some of the most violent events in the universe. These explosions were so powerful that they forged new elements: carbon, oxygen, silicon, iron, and dozens of others in their final moments. The explosions scattered these elements into space, enriching the surrounding gas clouds. This was crucial. The first stars seeded the universe with the raw materials needed to build everything else: planets, asteroids, and eventually, life. Every element heavier than helium in your body was forged inside a star or during a stellar explosion. You are, quite literally, made of stardust. As the first stars lived and died, something larger was taking shape. The clumps and structures that gravity had been building during the Dark Ages were getting bigger and more organized. Gas, dark matter, and the remnants of dead stars were coming together to form the first galaxies. These early galaxies were small by today's standards, irregular, chaotic collections of stars, maybe a few 100 million solar masses. They didn't have the beautiful spiral structures or orderly shapes we associate with galaxies today. They were rough and messy, but they were the beginning of something grand. What exactly is a galaxy? At its most basic, it's a gravitationally bound collection of stars, gas, dust and dark matter. But galaxies are more than just the sum of their parts. They're vast ecosystems where stars are born, live and die, where gas flows in and out, where black holes lurk at the centres, shaping the fates of billions of stars around them. By about 500 million years after the Big Bang, the universe was filling with these small galaxies. They formed in enormous numbers, and they didn't stay isolated for long. Gravity ensured that galaxies would attract each other, collide and merge. When two galaxies meet, they don't destroy each other. Instead, they combine, their stars passing by each other with room to spare, their gas clouds smashing together to trigger new bursts of star formation. Over time, small galaxies merge to form larger ones, and those larger galaxies merge to form larger ones still. This hierarchical process of galaxy growth continues to this day. It's how our own Milky Way galaxy formed, and it's how many of the giant galaxies we see today came to be. By 1 billion years after the Big Bang, the universe was beginning to look more familiar. Galaxies of various sizes dotted space, organized by gravity into larger structures, groups and clusters. The cosmic web, that vast network of filaments and voids that gives the universe its large-scale structure, was taking shape. The age of galaxies building the cosmic cities. Between 1 and 6 billion years after the Big Bang, the universe entered what might be called its golden age of galaxy formation and star formation. This was when the universe was most active, most productive, most violently creative. Star formation rates peaked during this era. Galaxies were forming stars at rates 10 or even 100 times faster than the Milky Way does today. Gas was abundant, collisions between galaxies were frequent, and the conditions were perfect for triggering enormous bursts of starbirth. Some of these galaxies were so active that scientists call them starburst galaxies. In a single year, a starburst galaxy might form hundreds or even thousands of new stars. Compare that to our own galaxy, which forms about 1 or 2 new stars per year on average. The difference is staggering. During this era, galaxies were also developing their characteristic shapes. Some became elliptical galaxies, smooth and featureless, their stars moving in random orbits. Others became spiral galaxies, with beautiful rotating disks and sweeping arms where new stars form. The shapes a galaxy takes depend on its history, how many collisions it's experienced, how much gas it has, how it's rotating, and at the centers of many galaxies, something dark and powerful was growing. Black holes. Actually, black holes come in different sizes, and it's the supermassive ones we're talking about here. Monsters with millions or billions of times the mass of our Sun. Evidence suggests that nearly every large galaxy has one of these supermassive black holes at its center. Our own Milky Way has one, with a mass of about 4 million suns sitting in the constellation Sagittarius. How did these supermassive black holes form? Scientists are still working out the details, but evidence suggests they grew from smaller seed black holes in the early universe, accumulating mass over billions of years. Some might have formed directly from collapsing gas clouds. Others might have started as massive stars that collapsed. Regardless of their origins, these black holes grew by feeding on surrounding gas and by merging with other black holes during galaxy collisions. When gas falls toward a supermassive black hole, it forms a swirling disk that heats up to millions of degrees, emitting enormous amounts of radiation. At their most active, these feeding black holes can outshine their entire host galaxy, appearing as brilliant beacons called quasars. The brightest quasars can be seen from billions of light years away, allowing us to study the early universe in detail. But black holes don't just consume matter, they also influence the evolution of their host galaxies. The energy they emit can heat surrounding gas, preventing it from cooling and forming new stars. This creates a kind of self-regulation. A galaxy forms stars rapidly, the black hole grows and becomes more active, and its energy output eventually slows down star formation. This delicate balance between growth and feedback has shaped the galaxies we see today. Our cosmic neighborhood takes shape, the Milky Way. Somewhere in this busy, star-forming universe, our own galaxy was coming together. The Milky Way galaxy didn't form all at once. Like other galaxies, it grew through a combination of gas accretion and mergers with smaller galaxies. Its history is written in the motions and compositions of its stars, and scientists are still working to read that history in detail. Evidence suggests that the Milky Way's oldest stars formed about 13 billion years ago, when the universe was less than 1 billion years old. These ancient stars are found in the galaxy's halo and in globular clusters, dense, spherical collections of stars that orbit above and below the main disk. Over the next several billion years, the Milky Way continued to grow. Smaller galaxies fell into it, their stars scattered throughout the larger structure. Gas flowed inward, settling into a rotating disk where new generations of stars formed. The spiral arms that give our galaxy its distinctive shape developed from density waves in this disk, regions where stars and gas crowd together, temporarily, as they orbit the galactic center. By about 10 billion years ago, the Milky Way had developed its basic structure. A central bulge packed with older stars, a thin disk where most star formation happens, and a sparse halo of ancient stars and globular clusters. This structure has evolved since then, but the basic architecture was in place. The galaxy wasn't alone. It was part of a small group of galaxies that would eventually become what we call the local group, a collection of about 80 galaxies, dominated by the Milky Way and the Andromeda Galaxy. These galaxies are bound together by gravity, slowly orbiting their common center of mass, and the local group itself is part of something even larger, the Laniakea supercluster, a vast structure containing about 100,000 galaxies spread across 500 million light-years. This is our address in the universe: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster. Dark energy takes over. The universe begins accelerating. About 6 billion years ago, something peculiar happened to the universe. Its expansion, which had been gradually slowing down due to the gravitational pull of all the matter it contained, began to speed up instead. This discovery, made in 1998 by two teams of astronomers studying distant supernovae, was completely unexpected. It earned a Nobel Prize and forced scientists to reconsider their understanding of the universe on the larger scales. What could cause the expansion of the universe to accelerate? The answer scientists arrived at is something called dark energy, though that name is really just a placeholder for something we don't yet understand. Dark energy appears to be a property of space itself, a kind of energy that's evenly distributed throughout the universe and that pushes space apart. The effect is subtle on small scales. You don't need to worry about dark energy pulling your body apart, but on cosmic scales, it's profound. Dark energy appears to make up about 68% of all the energy in the universe. Dark matter, the mysterious invisible substance that provides the extra gravity needed to hold galaxies together, makes up about 27%. Regular matter, the stuff you and I and all the stars are made of, constitutes only about 5% of the universe. Think about that. Everything we've ever seen, every star and planet and galaxy, every atom we've ever detected, makes up only a tiny fraction of what's out there. The universe is far stranger and more mysterious than it appears. As dark energy began dominating the universe's evolution, the rate of star formation started to decline. Why? Because dark energy's acceleration works against gravity, making it harder for gas to collapse and form new stars. The universe was entering a gradual decline from its peak productivity. The frantic pace of galaxy collisions and star formation that characterized earlier eras was slowing down. But this didn't mean the universe was becoming boring. Far from it. There was still plenty of activity, still plenty of drama. And in one unremarkable spiral arm of one medium-sized galaxy, something extraordinary was about to happen. A star is born. The sun's formation, about 4.6 billion years ago, in a quiet region of the Milky Way's Orion Arm, a cloud of gas and dust began to collapse. This wasn't unusual. Stars form this way all the time. But this particular collapse would lead to something special. The cloud, called a molecular cloud because of the molecules it contained, was made mostly of hydrogen and helium left over from the Big Bang, along with heavier elements forged in earlier generations of stars. It might have been triggered to collapse by the shock wave from a nearby supernova explosion, or perhaps just by its own gravity overcoming the internal pressure that had been holding it up. As the cloud collapsed, it began to spin faster, like a figure skater pulling their arms in during a pirouette. The material flattened into a disk with most of the mass accumulating at the center. That central accumulation grew hotter and denser as more material fell onto it, compressed by its own gravity. Eventually, the temperature and pressure at the center became so extreme that nuclear fusion ignited. Hydrogen atoms were crushed together to form helium, releasing enormous amounts of energy in the process. A new star was born, our sun had turned on, but the sun wasn't alone. Surrounding it was a disk of leftover material, gas and dust that hadn't fallen into the growing star. This protoplanetary disk would become our solar system. The birth of Earth, from dust to world. In the disk around the young sun, small particles of dust began sticking together. At first, these were microscopic grains, held together by static electricity and chemical bonds. But as these grains collided gently, they formed larger clumps. These clumps became pebbles, and pebbles became boulders, and boulders became mountains floating in space. This process, called accretion, continued for millions of years. The larger objects grew faster because their stronger gravity attracted more material. Eventually, some of these objects became planetesimals, small bodies anywhere from a few kilometers to a few hundred kilometers across. The planetesimals collided and merged, building ever larger bodies called protoplanets. The inner solar system, where it was too hot for ice to exist, developed rocky protoplanets. The outer solar system, beyond what scientists call the frost line, had protoplanets made of rock and ice. One of these rocky protoplanets, orbiting at just the right distance from the Sun, continued growing and sweeping up material from its orbit. About 4.5 billion years ago, it had grown large enough to be called a planet. This was the early Earth, though it looked nothing like the world we know today. The young Earth was a hellish place. It was bombarded constantly by leftover debris from planet formation. Each impact released enormous energy, keeping the surface molten. The planet glowed red hot, a sphere of liquid rock in the darkness of space. Then, about 4.4 billion years ago, something dramatic happened. Another protoplanet, roughly the size of Mars and sometimes called Theia, crashed into Earth. The impact was so violent that it vaporized parts of both bodies. Debris from the collision was thrown into orbit around Earth, and over time, this debris coalesced to form the Moon. This collision had profound effects. It tilted Earth's axis, giving us seasons. The debris that formed the Moon stripped away much of Earth's early atmosphere, and the impact probably remelted much of Earth's surface, resetting the planet's geological evolution. The Hadean Earth. Hell gives way to ocean. The period from Earth's formation to about 4 billion years ago is called the Hadean Eon, named after Hades, the Greek underworld. It was a fitting name for a time when Earth's surface was largely molten. But the Hadean Earth wasn't completely hellish. Evidence suggests that liquid water may have existed on the surface as early as 4.4 billion years ago, much earlier than scientists once thought. How is this possible? The young Earth would have had a thick atmosphere of carbon dioxide and water vapour, creating a greenhouse effect that kept the surface from freezing, even though the Sun was about 30% dimmer than it is today. As the bombardment gradually decreased and the surface cooled, water vapour condensed. It began to rain, and it rained for what must have been millions of years. As the sky slowly cleared, and oceans began to fill the low-lying basins of Earth's cooling crust. By 4 billion years ago, Earth probably had substantial oceans, a thick atmosphere, and a partly solid crust broken into early versions of tectonic plates. The planet was still violent, volcanic activity was intense, the atmosphere was toxic by modern standards, and the bombardment by asteroids and comets hadn't completely stopped. But the stage was set for something new. Somewhere in these early oceans, in conditions we're still trying to understand, chemistry became biology. Life emerged. The origin of life, from chemistry to biology. How did life begin on Earth? This is one of the most profound questions in science, and despite decades of research, we don't have a complete answer. What we do know is that by 3.8 billion years ago, and possibly earlier, Earth was home to living organisms. The earliest life would have been simple, single-celled organisms that we might classify as bacteria if we could see them today. They had no nucleus, no complex internal structures, just a membrane enclosing genetic material and the basic molecular machinery needed to survive and reproduce. But where did these first cells come from? Scientists have identified several key steps that were probably necessary. First, simple organic molecules, the building blocks of life, like amino acids and nucleotides, had to form. Experiments have shown this can happen naturally in conditions similar to early Earth, either in the atmosphere, in volcanic hot springs, or at hydrothermal vents on the ocean floor. Next, these building blocks had to assemble into more complex molecules like proteins and nucleic acids. RNA, which can both store genetic information and catalyze chemical reactions, might have played a key role. Some scientists think there was an RNA world where this molecule performed both functions before DNA and proteins took over. Finally, these molecules needed to be enclosed in a membrane, creating a boundary between the inside of the cell and the outside environment. Simple membrane-like structures can form spontaneously from certain lipid molecules in water, so this step might have been more straightforward than the others. The jump from non-living chemistry to living cells was gradual, with many intermediate steps. We may never know the exact pathway, but evidence suggests it happened relatively quickly after Earth became habitable. This has led some scientists to speculate that life might be relatively common in the universe, arising wherever conditions are suitable. For more than 1 billion years, life on Earth remained simple. Single-celled organisms lived in the oceans, metabolizing various chemicals and gradually changing their environment. Some learned to use sunlight for energy through photosynthesis, producing oxygen as a waste product. But oxygen was initially removed from the atmosphere by reactions with iron and other elements. Earth's atmosphere remained oxygen-free for a long time. The Great Oxidation, life changes. Everything around 2.4 billion years ago, something happened that would transform Earth forever. Oxygen began accumulating in the atmosphere. This event, called the Great Oxidation Event, was one of the most significant environmental changes in Earth's history. What caused it? Photosynthetic bacteria called cyanobacteria had been producing oxygen for hundreds of millions of years. But initially, this oxygen reacted with dissolved iron in the oceans, forming iron oxide that settled to the seafloor. You can still see evidence of this today in banded iron formations, distinctive layers of iron-rich rock. Eventually, the oxygen-absorbing capacity of the oceans was exhausted. The oceans became saturated with oxygen, and it began escaping into the atmosphere. Oxygen levels rose from essentially zero to perhaps a few percent of modern levels, and then later, after fluctuating for billions of years, to the roughly 21% we have today. This was a catastrophe for most life at the time. Oxygen is actually toxic to organisms that haven't evolved to deal with it. It causes chemical reactions that damage cells. The rise of oxygen probably caused a mass extinction of organisms adapted to the oxygen-free world. But this catastrophe created opportunities. Oxygen allowed for more efficient forms of metabolism. Organisms that could use oxygen to burn food molecules could extract far more energy than those using older metabolic pathways. This energy bonanza eventually made complex life possible. The Great Oxidation Event also changed Earth's surface chemistry. Oxygen reacted with methane in the atmosphere, a powerful greenhouse gas. Some scientists think this caused a severe ice age, possibly the first snowball Earth event where ice covered most or all of the planet's surface. Life somehow survived these harsh conditions, perhaps in refuges near volcanoes or in the deep ocean. The origin of complex cells. Eukaryotes appear. For billions of years after life began, all organisms were prokaryotes, simple cells without nuclei or complex internal structures. Then about 2 billion years ago, something remarkable happened. A new kind of cell appeared, the eukaryote. Eukaryotic cells are fundamentally different from prokaryotic cells. They're larger, more complex, and contain specialized internal compartments called organelles. The nucleus houses the cell's DNA. Mitochondria produce energy. In plant cells, chloroplasts perform photosynthesis. These organelles work together in sophisticated ways, allowing eukaryotic cells to do things prokaryotic cells can't. How did eukaryotes evolve? The leading explanation is endosymbiosis, one cell living inside another. Evidence suggests that mitochondria and chloroplasts were once free-living bacteria that were engulfed by a larger cell. Instead of being digested, they survived inside, and over millions of years, they became permanent residents, losing their independence but contributing vital functions. This is an astonishing idea when you think about it. The powerhouses of your cells, the mitochondria that provide you with energy, are the descendants of ancient bacteria that were incorporated into your ancestors' cells more than 1 billion years ago. They even retain their own DNA, separate from the DNA in your cell nucleus, and they reproduce independently within your cells. The evolution of eukaryotic cells was a crucial step toward complex life. All multicellular organisms, plants, animals, fungi, are made of eukaryotic cells. Without this evolutionary innovation, Earth might still be a planet of nothing but bacteria and archaea. But even after eukaryotes appeared, life remained mostly single-celled for another 1 billion years. Multicellular organisms did exist. There's evidence of algae-like multicellular life from about 1.6 billion years ago, but complex multicellular life was still a long way off. Snowball Earth. When the world froze. Between about 720 and 580 million years ago, Earth experienced at least 2, and possibly more, extreme ice ages. These weren't ordinary ice ages where glaciers advance and retreat. Evidence suggests that ice covered the entire planet, from pole to pole, including the oceans. These events are called Snowball Earth episodes. Imagine Earth as a frozen ball of ice and snow, reflecting most of the sun's light back into space. Temperatures at the equator might have been similar to Antarctica today. The oceans were covered with ice perhaps 1 kilometre thick. Photosynthesis would have nearly stopped, and life would have been pushed to the edge of extinction. How did this happen? Scientists think a runaway cooling process was responsible. Ice reflects sunlight better than rock or water. So as ice formed, Earth reflected more sunlight, which caused more cooling, which caused more ice formation. Normally this runaway process is prevented by the greenhouse effect, but something, perhaps a lack of volcanic activity or unusual continental arrangements, allowed the cooling to spiral out of control. How did Earth escape from this frozen state? Volcanoes. Even when the surface was frozen, volcanoes continued erupting, slowly adding carbon dioxide to the atmosphere. With the oceans frozen and unable to absorb this gas, and with almost no weathering of rocks to remove it, carbon dioxide built up over millions of years. Eventually, the greenhouse effect became so strong that ice began to melt. Once melting started, the process reversed. Less ice meant less reflection of sunlight, which meant more warming, which meant more melting. The transition from Snowball Earth to a warm world might have been rapid in geological terms, perhaps just a few thousand years. And in the aftermath, as life recovered and diversified in the newly warm oceans, something unprecedented happened. Complex multicellular life exploded onto the scene. The Cambrian explosion. Life gets complicated. Around 541 million years ago, at the beginning of a period called the Cambrian, the fossil record suddenly becomes much richer. Animals with hard shells and skeletons appear in abundance, and the diversity of body plans expands dramatically. This is the Cambrian explosion, one of the most significant events in the history of life. What caused this rapid diversification? Scientists don't have a single answer, but several factors probably contributed. Oxygen levels in the atmosphere and oceans had risen high enough to support active, mobile animals. The evolution of predation created an evolutionary arms race, with predators developing better ways to catch prey and prey developing better ways to escape. The evolution of hard body parts, shells and skeletons, provided both protection and support, allowing animals to grow larger and more diverse. During the Cambrian, most of the major animal groups we see today appeared. Arthropods, the ancestors of insects, spiders, and crustaceans, evolved into countless forms. Mollusks developed shells. Chordates, the group that includes all vertebrates, appeared as small fish-like creatures called lancelets and strange animals like picaia. The oceans filled with an alien menagerie of creatures. There was a Nomalocaris, a metre-long predator with compound eyes and grasping appendages. There was Opabinia, with 5 eyes and a long flexible proboscis. There was Hallucigenia, so strange that scientists initially reconstructed it upside down and backward. On land things were quieter. Plants hadn't yet colonized the continents. The land was barren rock and sand, with perhaps some bacterial mats in wet areas. But the stage was being set for the next great expansion of life. Life invades the land, plants and animals. The colonization of land was one of life's greatest challenges. The ocean provides buoyancy, stable temperatures, and protection from ultraviolet radiation. Land offers none of these advantages. For life to succeed on land, organisms needed new adaptations. Plants led the way, venturing onto land around 470 million years ago. The earliest land plants were simple, moss-like organisms that stayed close to water. But they had a crucial innovation, a waxy coating that prevented them from drying out. Over millions of years, plants evolved roots to anchor themselves and absorb nutrients, vascular tissues to transport water and nutrients throughout their bodies, and eventually, leaves and seeds. By about 400 million years ago, the first forests had appeared. These weren't forests of flowering trees like we see today. Flowering plants wouldn't evolve for another 250 million years. These were forests of ferns, horsetails, and early seed plants. Some, like the tree-like plant Archaeopteris, grew more than 30 meters tall. Animals followed plants onto land. Arthropods, with their already existing hard exoskeletons, were well suited to terrestrial life. Millipedes and early insects were among the first land animals. Amphibians evolved from lobe-finned fish around 365 million years ago, developing legs that allowed them to walk on land, while still returning to water to reproduce. The transformation of the land was profound. Soil developed as plants broke down rock with their roots, and bacteria decomposed organic matter. The atmosphere's oxygen levels rose further, supported by the photosynthesis of all these new land plants. Earth's green, vegetated continents began to resemble the planet we know today. The age of reptiles, dinosaurs rule. By about 320 million years ago, the first reptiles had evolved from amphibian ancestors. Reptiles had a key advantage over amphibians. They laid eggs with tough, waterproof shells that could survive on land. This freed reptiles from dependence on water for reproduction and allowed them to colonize even dry environments. Reptiles diversified rapidly. Some became small and adapted to eating insects. Others grew large and became fearsome predators. One group, the therapsids, evolved features that would eventually characterize mammals. Another group, the archosaurs, would give rise to dinosaurs. The first dinosaurs appeared about 230 million years ago, during the Triassic period. They were relatively small, dog-sized or smaller, and not particularly dominant, but over millions of years they evolved into an astounding variety of forms. There were the long-necked sauropods, some weighing more than 70 tons, the largest land animals that ever lived. There were fierce predators like Tyrannosaurus rex, with bone-crushing jaws and teeth the size of bananas. There were swift, intelligent hunters like Velociraptor. There were armoured herbivores, covered in bony plates and spikes. There were dinosaurs with elaborate head crests, horns and frills. For more than 160 million years, dinosaurs dominated terrestrial ecosystems. They evolved to fill nearly every ecological niche on land. Some even returned to the water or took to the air. Birds, which we now recognise as living dinosaurs, evolved from small feathered theropods around 150 million years ago. While dinosaurs ruled the land, other reptiles dominated different environments. Pterosaurs, not dinosaurs but close relatives, mastered flight and grew to enormous sizes, some with wingspans exceeding 10 meters. Marine reptiles like ichthyosaurs and plesiosaurs filled the oceans, becoming the apex predators of their time. Meanwhile, mammals existed throughout this period, but they remained small and mostly nocturnal, living in the shadows of the dinosaurs. They survived by staying out of the way, occupying niches that dinosaurs couldn't exploit. They were biding their time, and then, 66 million years ago, everything changed. The day the dinosaurs died, the KT extinction. It was an ordinary day in what's now the Yucatan Peninsula of Mexico. The sun rose over warm, shallow seas. Dinosaurs grazed on coastal plains. Life continued as it had for millions of years. Then at tremendous speed, an asteroid roughly 10 kilometers across, about the size of a mountain, slammed into Earth. The impact released energy equivalent to billions of nuclear weapons. It vaporized the asteroid instantly and excavated a crater more than 180 kilometers wide. Rock and debris were thrown into the atmosphere at such speeds that they escaped Earth's gravity and then rained back down, heating the atmosphere to oven-like temperatures across the entire planet. If you were standing on the other side of the world, you might have had several hours before you felt the effects, but when they came, they were catastrophic. The sky darkened with debris, massive earthquakes shook the ground. Tsunamis hundreds of meters high swept across coastlines. Wildfires ignited across multiple continents as superheated debris fell from the sky. But the immediate effects, as terrible as they were, weren't the worst part. The impact threw so much dust and soot into the atmosphere that it blocked out sunlight for months or even years. Photosynthesis stopped. Temperatures plummeted. The food chain collapsed from the bottom up. About 75% of all species on Earth went extinct, including all non-avian dinosaurs. The giant marine reptiles died out. The pterosaurs disappeared. Most of Earth's forests burned and didn't recover for centuries. It was one of the worst mass extinctions in the planet's history, but life is resilient. Some organisms survived. Mammals, small and adaptable, made it through. Birds, the dinosaurs that had taken to the sky, survived. Crocodiles and turtles survived. Fish and amphibians survived. Plants held on as seeds and roots buried in the soil. And in the aftermath, with the dinosaurs gone and ecological niches suddenly vacant, the survivors had opportunities to diversify and evolve into new forms. The age of dinosaurs was over. The age of mammals was beginning. The rise of mammals, our ancestors, take centre stage. In the immediate aftermath of the KT extinction, Earth was a devastated world, but it recovered, as it always does. Within a few million years, forests had regrown, ecosystems had stabilised, and life was flourishing again, but with a different cast of characters. Mammals, no longer constrained to small body sizes and nocturnal lifestyles, began diversifying rapidly. Within 10 million years of the extinction, mammals had evolved into numerous forms, filling niches previously occupied by dinosaurs. Some mammals became herbivores of various sizes, from tiny rodents to massive browsers. Others became predators, developing the speed and weaponry needed to catch prey. Some returned to the oceans, eventually becoming whales and dolphins. Others took to the air, becoming bats, the only mammals besides extinct pterosaurs to achieve powered flight. By about 50 million years ago, most of the major groups of modern mammals had appeared. There were early horses, no bigger than dogs. There were the ancestors of elephants, whales, and primates. The world was warming. This was the Paleocene-Eocene thermal maximum, possibly the warmest the planet has been in the last 100 million years. Palm trees grew in Wyoming. Crocodiles lived in the Arctic. Around this time, in tropical forests, a group of mammals called primates was thriving. These were the ancestors of all modern primates, including monkeys, apes, and humans. They were small, tree-dwelling creatures with forward-facing eyes for judging distances, grasping hands for holding branches, and relatively large brains for their body size. Over millions of years, primates diversified. Some remained small and nocturnal. Others grew larger and became active during the day. By about 25 million years ago, the first apes had evolved in Africa. They were tailless primates that moved through trees by swinging from branches, different from monkeys that ran along the tops of branches. These early apes continued evolving and diversifying. Around 16 million years ago, the lineage that would lead to orangutans split off. Around 8 million years ago, the lineage leading to gorillas split from our own. And somewhere between 5 and 7 million years ago, in the forests and woodlands of Africa, our lineage separated from the one that would become chimpanzees and bonobos. The stage was set for the most recent chapter of our story, the evolution of humans. The human story begins. Walking upright. What makes a human? This question doesn't have a simple answer. The evolutionary transition from ape-like ancestors to modern humans was gradual, with many intermediate forms that blur the boundary between ape and human. But one of the earliest and most significant changes was bipedalism, walking upright on two legs. Evidence suggests that our ancestors began walking upright at least 6 million years ago, and possibly earlier. Fossils of Sahelanthropus tchadensis, dating to about 7 million years ago, show features suggesting this species could walk upright, though it also spent time in trees. Why did our ancestors start walking on two legs? Scientists have proposed numerous explanations. It might have been more energy efficient for travelling across open grasslands. It might have freed the hands for carrying food or tools. It might have helped them see over tall grass to spot predators. It might have been useful in displays or to reduce exposure to the midday sun. The true reason was probably a combination of several factors. By about 4 million years ago, species like Australopithecus afarensis, famously represented by the fossil Lucy, were accomplished bipeds. They walked upright habitually, though they still had long arms and curved fingers, suggesting they climbed trees regularly. Their brains were still quite small, only about 1/3 the size of a modern human brain. For millions of years, our ancestors remained relatively ape-like in many respects. They had small brains, large teeth for processing tough plant foods, and probably limited use of tools. But around 2.5 to 3 million years ago, things began to change more rapidly. The first tools, technology emerges. Around 3.3 million years ago, in what's now Kenya, someone picked up a rock and struck it against another rock, deliberately creating a sharp edge. This simple act marks the beginning of human technology, the earliest evidence we have of our ancestors making tools. These earliest tools were crude, just rocks with sharp flakes knocked off. but they represented something profound. They showed planning, an understanding of cause and effect, and the ability to modify the environment rather than just adapting to it. By 2.6 million years ago, stone tools had become more standardized, appearing at multiple sites across East Africa. This marks the beginning of what archaeologists call the Oldowan tool industry, named after Olduvai Gorge in Tanzania, where many examples were found. These tools would remain largely unchanged for nearly 1 million years. What were these tools used for? Evidence suggests they were used to process animal carcasses, cutting meat from bones, smashing bones to access marrow. This dietary shift toward more meat and fat would have important consequences. Meat is a concentrated source of calories and nutrients, and it may have supported the evolution of larger brains. Around 2 million years ago, a new group of hominins appeared in Africa, the genus Homo, our own genus. Species like Homo habilis and Homo erectus had significantly larger brains than earlier hominins and were sophisticated tool makers. Homo erectus, in particular, was a game changer. Homo erectus was taller, with longer legs suited for long-distance walking and running. They made more sophisticated tools, including the teardrop-shaped hand axes that would remain in use for more than 1 million years. And crucially, Homo erectus was the first hominin to leave Africa, spreading across Asia and possibly into Europe. Fossils of Homo erectus have been found in China, Indonesia, and the Republic of Georgia, showing that by 1.8 million years ago, our ancestors had begun exploring the wider world. Fire, language, and culture becoming more human. Somewhere along the way, the exact timing is debated, our ancestors learned to control fire. Evidence of controlled fire use dates back to at least 1 million years ago, and possibly earlier. This was transformative. Fire provided warmth, allowing our ancestors to survive in colder climates. It provided protection from predators. Most importantly, it allowed cooking. Cooked food is easier to digest and provides more calories than raw food. This dietary improvement may have supported further brain growth and reduced the time spent chewing, freeing up time for other activities. Around the fires, social bonds would have strengthened, stories might have been told, knowledge would have been shared. Fire created a gathering place, a centre for community. But when did language emerge? This is one of the most contentious questions in paleoanthropology, because language doesn't fossilize. We can infer from brain structure that our ancestors had the neural capacity for language, and from throat anatomy that they could produce the sounds, but pinpointing when true language emerged is difficult. Most scientists think that basic forms of language probably existed by at least 500,000 years ago, and possibly much earlier. Complex language, with the full grammatical sophistication of modern languages, probably emerged sometime in the last 200,000 years, though some researchers argue for earlier dates. Language would have been revolutionary. It allows the transmission of complex information. It allows planning and coordination. It allows teaching abstract concepts. It creates culture, shared knowledge, beliefs, and practices that are passed from generation to generation. By several 100,000 years ago, our ancestors were unambiguously cultural beings. They made sophisticated tools requiring multiple steps to manufacture. They used pigments, suggesting symbolic thought. They cared for the sick and elderly. They buried their dead, sometimes with grave goods. Different populations developed different tool traditions, different ways of doing things, cultural diversity that mirrors what we see in modern humans. The roots of human culture run deep. Modern humans emerge, Homo sapiens. Somewhere between 300,000 and 200,000 years ago in Africa, a population of archaic humans evolved into anatomically modern humans. Homo sapiens, our species. The fossils from Jebel Irhoud in Morocco dating to about 315,000 years ago, show a mix of archaic and modern features, suggesting we were in the midst of transitioning to our modern form. By 200,000 years ago, humans with essentially modern anatomy existed in East Africa. But anatomy is only part of the story. Behavioural modernity, the full package of traits we associate with humans today, may have taken longer to develop. For tens of thousands of years, Homo sapiens remained in Africa, living alongside other species of humans, like Homo heidelbergensis and Homo naledi. But starting around 70,000 to 60,000 years ago, groups of Homo sapiens began leaving Africa in significant numbers, spreading across the world. What prompted this expansion? Was it population pressure? Climate change? Some cognitive breakthrough? We don't know for certain. What we do know is that these migrating humans carried with them sophisticated tools, symbolic culture, and adaptability that would allow them to colonize nearly every habitat on Earth. As they spread, they encountered other human species that had left Africa earlier. In the Middle East and Europe, they met Neanderthals. In Asia, they met Denisovans and possibly Homo erectus populations. In Southeast Asia, they might have encountered Homo floresiensis, the hobbit humans of Indonesia. These encounters didn't always end peacefully, but they weren't always violent either. We know this because modern humans interbred with both Neanderthals and Denisovans. If you're of European or Asian descent, about 2% of your DNA comes from Neanderthals. If you're from Melanesia, you might carry up to 5% Denisovan DNA. We carry our cousins within us. By 40,000 years ago, Homo sapiens had reached Europe. By 30,000 years ago, they were in the Americas. By 3,000 years ago, they had colonized nearly every island in the Pacific. Humans had become a truly global species, and along the way, something remarkable happened. The archaeological record suddenly becomes rich with art. Cave paintings appear in France, Spain and Indonesia, some dating back more than 40,000 years. Carved figurines, musical instruments, elaborate jewellery, all signs of a fully modern human mind, engaged in symbolic thought and creative expression. Our ancestors were leaving messages. They were saying, "We were here, we existed, we thought and felt and wondered." And thousands of years later, we're still reading those messages, still connecting with those ancient humans who were, in every meaningful way, just like us. The agricultural revolution. Humans reshaped the world. For more than 95% of our species' history, we were hunter-gatherers. We lived in small groups, moving with the seasons, following game, gathering plants. Then starting about 12,000 years ago in the Middle East, something changed. People began deliberately planting seeds and tending crops. They began domesticating animals, keeping them close rather than hunting wild populations. Agriculture was born. This wasn't a sudden revolution. The transition from hunting and gathering to farming took thousands of years and happened independently in several places. The Middle East, China, Mesoamerica, the Andes, and parts of Africa. In each place, people domesticated different plants and animals suited to their environment. Wheat and barley in the Middle East, rice in China, corn, beans, and squash in Mesoamerica, potatoes in the Andes. Why did this transition happen? Climate change played a role. The end of the last ice age created conditions more favourable for plant growth. But humans also played an active role, selecting seeds from plants with desirable traits, gradually transforming wild species into domesticated crops. Agriculture allowed larger populations. A plot of farmland can support far more people than the same area of wilderness. Villages grew into towns, towns into cities. By 6,000 years ago, the first true cities had appeared in Mesopotamia, with populations in the thousands. But agriculture came with costs. Early farmers worked harder and had less diverse diets than hunter-gatherers. They were more vulnerable to famine if crops failed. They lived in denser populations where diseases could spread more easily. Skeletons from early agricultural societies show signs of malnutrition and disease more commonly than those from hunter-gatherer populations. Yet agriculture won out. Why? Probably because agricultural societies could support larger populations and more complex social structures. They could field larger armies. They could support specialists, people who didn't produce food but instead made tools, built buildings, kept records, or organized society. And they did keep records. Around 5,000 years ago, in Mesopotamia and Egypt, people began using symbols to represent words and numbers. Writing was invented. For the first time, humans could preserve information beyond what could be passed down orally. Knowledge could accumulate across generations in a new way. History, in the sense of written records, had begun. Civilizations rise and fall. The last 5,000 years. From this point forward, human history accelerates. The pace of change, which had been slow for millions of years, begins to quicken. Great civilizations rose around the world. The Egyptians built pyramids and developed hieroglyphic writing. The Sumerians created the first writing system, cuneiform, pressed into clay tablets. The Indus Valley Civilization developed sophisticated cities with advanced plumbing and urban planning. In China, dynasties rose and fell, leaving behind bronze vessels, oracle bones, and eventually elaborate palaces and tombs. Across the ocean, unaware of these old-world civilizations, the Maya built cities in the jungles of Central America, developed a sophisticated calendar, and created one of the few writing systems invented independently anywhere in the world. In South America, the Inca would eventually build an empire stretching thousands of miles along the Andes. These civilizations discovered mathematics, astronomy, philosophy, art, and architecture. They developed legal codes, religious systems, and forms of government. They traded goods across vast distances. They made war on each other with increasing sophistication. And they fell. Civilizations proved fragile. The Maya cities were largely abandoned by 900 CE for reasons still debated: drought, warfare, environmental degradation, or some combination. The Western Roman Empire collapsed in the 5th century CE, fragmenting Europe into smaller kingdoms. Dynasties in China rose and fell in cycles. The pattern repeated across the world. Growth, peak, decline, but knowledge accumulated despite, and sometimes because of, these cycles. Each civilization built on what came before, adding its own innovations. Mathematics advanced from simple counting to algebra, calculus, and beyond. Astronomy evolved from naked eye observations to sophisticated models of planetary motion. Technology improved from bronze to iron to steel. The scientific revolution, understanding the cosmos. For most of human history, we explained the world through mythology and religious narratives. The universe was mysterious, governed by gods or other supernatural forces beyond human understanding. But starting in the 16th and 17th centuries in Europe, a new approach gained traction. Thinkers like Copernicus, Galileo, Kepler, and Newton began applying mathematics and systematic observation to natural phenomena. They proposed that the universe operated according to natural laws that humans could discover and understand. This scientific revolution changed everything. Copernicus showed that Earth wasn't the center of the universe. We orbited the sun, not the other way around. Galileo turned the newly invented telescope to the sky and discovered moons orbiting Jupiter, showing that not everything orbited Earth. Newton developed laws of motion and gravity that explained both falling apples and orbiting planets with the same mathematical framework. For the first time, humans could make accurate predictions about natural phenomena, based on mathematical laws rather than supernatural explanations. And these predictions worked. They could be tested, verified, refined. The scientific method, observation, hypothesis, experiment, conclusion, proved extraordinarily powerful. Applied to chemistry, it revealed the elements and how they combine. Applied to biology, it led to the discovery of cells, DNA, and evolution. Applied to geology, it revealed Earth's ancient history. Applied to physics, it exposed the fundamental forces and particles that make up reality. Each discovery raised new questions. Each answer opened new mysteries. The more we learned, the more we realized how much we didn't know. But the trajectory was clear. Humans were beginning to understand the cosmos, to read the story of the universe written in starlight and stone. The Industrial Revolution, energy and transformation. In the late 18th century, beginning in Britain, humans began harnessing new energy sources on an unprecedented scale. The invention of the steam engine allowed us to convert the energy stored in coal into mechanical work. This was the beginning of the Industrial Revolution. The effects were profound. Factories appeared, mass-producing goods that previously had been made by hand. Railways crisscrossed continents, moving people and goods faster than ever before. Ships no longer depended on wind alone. Cities swelled as people moved from farms to factories. The Industrial Revolution brought tremendous material wealth to industrialized nations. Living standards rose. Life expectancy increased. Literacy spread as education became more common. But it also brought pollution, exploitation of workers, widening inequality, and the beginning of humanity's massive impact on the global climate. Through the 19th and 20th centuries, the pace of technological change accelerated further. Electricity transformed daily life. The internal combustion engine made cars and airplanes possible. Radio and television changed how information spread. Antibiotics and vaccines conquered diseases that had killed millions. Computers, at first room-sized machines, shrank to fit on desks, then in pockets. In 1969, less than a century after powered flight was first achieved, humans landed on the moon. We had left Earth, our home for all of our species' existence, and walked on another world. As astronauts looked back at Earth from the lunar surface, they saw our planet as it truly is, a small blue marble hanging in the darkness of space, the only home we've ever known. The modern era, Anthropocene and beyond. Today we live in a world transformed by human activity. Our impact on the planet is so significant that many geologists propose we've entered a new geological epoch, the Anthropocene, the age of humans. We've altered the surface of the planet more than any other species. We've dammed rivers, leveled mountains, cleared forests. We've driven countless species to extinction and spread others around the globe. We've changed the chemistry of the atmosphere, adding carbon dioxide and other greenhouse gases at a rate not seen in millions of years. The consequences of this are now becoming clear. Earth's average temperature is rising, ice caps are melting, sea levels are climbing, weather patterns are shifting. These changes pose risks to ecosystems and human societies worldwide. But humans are also uniquely capable of understanding and addressing these challenges. We can study the climate system, model future scenarios, and develop technologies to reduce our impact. We can choose to change course. Today, human population stands at about 8 billion people. We're connected in ways our ancestors couldn't have imagined, with information traveling around the world in seconds. We've developed medicine that can cure diseases that were once death sentences. We've created art, music, literature, and philosophy that enrich our lives in countless ways. We've also developed the ability to destroy ourselves through nuclear weapons, through environmental destruction, through engineered pathogens. The same science and technology that has given us unprecedented power and prosperity has also given us unprecedented responsibility. we stand at a unique moment in the cosmic timeline. We're the universe's way of knowing itself, conscious beings able to study our own origins, to trace the path from the Big Bang to the present moment. We're the only species we know of that can understand its place in the cosmos. And we're still evolving, still changing, still creating our story. The question is, what will we do with this understanding? How will we shape the next chapter? Looking forward. The deep future. What does the future hold? No one can say for certain, but we can make some educated guesses based on what we know. In the short term, the next few centuries, humanity's choices will determine whether we thrive or struggle. Will we address climate change effectively? Will we spread beyond Earth, establishing permanent settlements on other worlds? Will we develop technologies that improve life for everyone? Or will inequality continue to grow? These questions will shape the near future. Looking further ahead, the story becomes more speculative, but fascinating to consider. In about 1 billion years, the sun will have brightened enough that Earth's oceans will begin to evaporate. Complex life on Earth's surface will become impossible. If humanity or our descendants still exist, they'll need to have moved elsewhere. In about 4 billion years, our Milky Way galaxy will collide with the Andromeda Galaxy. This sounds catastrophic, but galaxies are mostly empty space. Individual stars likely won't collide, but the galaxies will merge over hundreds of millions of years, forming a larger elliptical galaxy. If Earth still exists and if anyone is around to see it, the night sky will be spectacular as the two galaxies interpenetrate. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin fusing helium. It will swell into a red giant, growing so large that it will likely engulf Mercury, Venus, and possibly Earth. If Earth survives, it will be a scorched, lifeless cinder. The sun will then shed its outer layers and collapse into a white dwarf, a dense, cooling ember about the size of Earth. On even longer timescales, the cosmos itself evolves. Star formation will continue for trillions of years, though at an ever-decreasing rate as the universe expands and gas becomes more dispersed. Eventually, perhaps 100 trillion years from now, the last stars will burn out. The universe will enter an era of cooling brown dwarfs and black holes. On incomprehensibly long timescales, 10 to the power of 100 years or more, even black holes will evaporate through a process called Hawking radiation. The universe will approach a state of maximum entropy, with all energy evenly distributed, too diffuse to do useful work. This is the heat death of the universe, an endpoint that's bleak in one sense, but also peaceful. The universe will have finally reached equilibrium. But these timescales are so vast, they're almost meaningless. They dwarf the entire history of the universe so far by factors too large to comprehend. And who knows what might happen in the meantime? Perhaps intelligence, whether human or something that evolves from us or something entirely separate, will find ways to survive and thrive that we can't currently imagine. The cosmic perspective. So here we are, at the end of our journey through 13.8 billion years. We started with an infinitesimal point of infinite density and energy, and we've arrived at this moment, with you watching or listening to these words. Think about the improbability of your existence. Your atoms were forged in stars that exploded billions of years ago. Those atoms drifted through space, came together in a cloud that collapsed to form our solar system, assembled into a planet, and through a process of chemistry and evolution spanning 4 billion years, organized themselves into you. You are a way for the universe to know itself. You're made of star stuff, as Carl Sagan famously said. But you're also more than that. You're conscious. You can contemplate your origins. You can appreciate beauty. You can ask questions about meaning and purpose. You can choose your actions. In all the billions of galaxies with their hundreds of billions of stars each, we don't yet know if there are others like us, other conscious beings wondering about their place in the cosmos. Maybe consciousness is common, maybe it's rare, maybe we're alone. We don't know yet. But what we do know is that here, on this small world orbiting an ordinary star in an unremarkable part of the galaxy, something remarkable happened. Matter became conscious. The universe woke up and started looking at itself. And that consciousness has discovered its own history. Through patient observation and brilliant reasoning, we've reconstructed the story of everything. From the first moments after the Big Bang to the formation of stars and galaxies. From the birth of our sun and earth to the emergence of life. From the first simple cells to the complex ecosystems and civilizations of today. We've learned that we're part of a continuous chain stretching back to the beginning. Every living thing on Earth shares a common ancestor. Every atom in your body has a cosmic history. You're connected to everything that's ever been, and you're connected to everything that exists now. This knowledge can be humbling. We're so small in the grand scheme of things, living on a pale blue dot in an incomprehensibly vast universe. But it can also be empowering. We're part of something magnificent. We're the universe's way of understanding itself, and we have the capacity to shape our future, to leave our mark, to create meaning in a cosmos that might otherwise have none. The story of the universe is still being written. New chapters unfold every day, as stars are born and die, as galaxies collide and merge, as potentially billions of worlds orbit their suns. And on at least one of those worlds, ours, conscious beings are pondering all of this, telling each other stories, creating art and music, building civilizations, reaching for the stars. What happens next? That depends partly on the impersonal forces of physics, gravity, thermodynamics, the expansion of space. But it also depends on us, on the choices we make, individually and collectively. We're no longer passive observers of the cosmic story. We're active participants with the power to influence how at least this small part of the story unfolds. So as we close this tour through cosmic time, take a moment to appreciate the journey. You've travelled from the Big Bang to the present moment. You've witnessed the birth of matter, the formation of stars and galaxies, the emergence of life, and the rise of consciousness. You've seen how atoms forged in stellar furnaces became planets, oceans, forests, animals, and people. And you've seen that this isn't just ancient history, it's your history. You're the current chapter in a story that began 13.8 billion years ago. Everything that came before made you possible. The first stars had to form to create the elements in your body. Earth had to form and develop oceans where life could emerge. Life had to survive countless catastrophes and evolutionary dead ends to produce the particular lineage that led to you. The odds of any particular person existing are astronomically small. But here you are against all odds, a conscious pattern of atoms contemplating your origins and your place in the cosmos. What will you do with this knowledge? How will you live your brief flicker of existence in the vast sweep of cosmic time? These aren't questions I can answer for you, but I hope this journey has given you a deeper appreciation for the extraordinary story you're part of, and perhaps a sense of wonder at the improbable, magnificent universe we inhabit. The cosmic timeline continues. New stars are forming right now. Galaxies are colliding. Somewhere in the universe, perhaps, life is emerging on other worlds, beginning its own evolutionary journey. The story goes on, and for now, on this small blue world, you're here to witness it and be part of it. Make it count. Thank you for joining me on this journey through time. Until next time, keep looking up. Keep asking questions and keep marveling at the cosmos that made us all possible.